2 in the morning, after the rain has stopped, a thin sheet of water spreads across an empty street, glistening under the lights. But it isn't rainwater, and it has no visible source. Somewhere below the asphalt, a buried pipe has cracked. The water is rising up through the soil, but the break could be right here, or 50 meters down the line. You can't see it. You can't dig blind across a whole street to chase it. So the city does something stranger. It listens. This is how a city hears its own wounds. First, the scale. Nearly 1 in 5 gallons of clean, treated drinking water never reaches a single tap. It's already been filtered, pumped, and pressurized, paid for, and then it vanishes underground before anyone can use it. Utilities call it non-revenue water. And most of it isn't a billing error. It's real, physical loss, leaks and bursts. In the United States alone, that waste costs water utilities an estimated $6.4 billion a year. Worldwide, about a third of all treated water is lost this way. To picture it, America loses about 6 billion gallons of treated water every single day, enough to fill 9,000 Olympic swimming pools. And somewhere, a water main is breaking every 2 minutes. And it's quiet. A single crack the width of a pencil under pressure can bleed thousands of gallons a day for months without ever reaching the surface. You cannot dig up an entire city to find a hole that small. So, more than a century ago, engineers asked a different question. Not where can we see it, but where can we hear it? The oldest tool for the job is also the simplest, a metal rod. One end presses against a fire hydrant or a valve, anything bolted to the pipe. The other end goes to your ear. It's a design essentially unchanged for over a century. Leak noise travels up through the metal. A small resonant chamber in the handle amplifies it, and a trained surveyor on a quiet night can literally hear the hiss of water escaping through the ground, through steel, into their ear. Later came aquaphones, electronic listening sticks, and ground microphones that sweep the surface above the pipe, hunting for the loudest point. It became a two-phase craft. First, a survey, walking the line, listening at every contact point to narrow the leak down to one suspect stretch. Then, pinpointing, zeroing in on the exact spot. But the human ear has limits. Traffic, footsteps, the city's own hum, all of it fights the faint signal. To go further, engineers had to understand the sound itself. So why does a leak make noise at all? Inside a water main, the pressure is high, typically 3 to 5 times atmospheric. When the pipe cracks, water doesn't seep. It jets violently through the opening. That jet is chaos. Turbulence tears at the edges of the crack. The escaping water drums against the soil, and the pipe wall itself vibrates. Together, they generate a continuous broadband hiss. And here's the key. That vibration doesn't stay put. It races along the pipe wall and through the water inside it for hundreds of meters in a metal pipe. The pipe becomes a telephone line. The leak is the voice on the other end, and it's speaking in both directions at once toward every sensor you might attach. You might think the loudest spot is the leak, sometimes, but sound bounces, fades, and lies about distance. Loudness can't pinpoint a leak. Timing can. Which brings us to the instrument that changed everything, the leak noise correlator. Clamp 2 sensors onto 2 access points, one on each side of the suspect stretch, 2 hydrants, 2 valves. Each one listens to the pipe. Both sensors hear the very same hiss, but the leak is closer to one of them, so that sensor hears each ripple of noise a fraction of a second before the other. The correlator finds that fraction. It slides the 2 recordings past each other, looking for the offset where they snap into alignment. That offset is the time delay, delta t. And once you know del t, geometry does the rest. The distance to the leak from the first sensor is the sensor spacing, minus the speed of sound times the delay, all divided by 2. Put in numbers. 200 meters between sensors. Sound traveling at 1,200 meters per second in this pipe. a measured delay of 50 milliseconds. The leak sits exactly 70 meters from sensor A. If that logic feels familiar, it should. It's the same trick your own brain runs constantly, comparing the tiny delay between your two ears to tell you which direction a sound came from. The correlator is just a city-sized pair of ears. And still, not a single shovel has touched the ground. But that elegant equation hides a trap. One number has to be exactly right. V, the speed of sound inside the pipe. Get V wrong, and the leak moves on you. A 10% error in the speed can shift your answer by meters, enough to dig in the wrong place. And V is not a constant. It depends on what the pipe is made of and how wide it is. In hard metal, sound is fast. In soft material, it crawls. So correlators carry lookup tables of known pipe speeds. And when the pipe material is uncertain, crews measure the speed right there on the street before they trust the answer. In cast iron or steel, leak noise can travel at well over a kilometer every second. Precision in, precision out. The same lesson as every measurement in this series. The correlator can feel like magic. 2 sensors, a sliver of time, and a precise X painted on the road. But it isn't magic, and a good crew knows exactly where their instrument goes deaf. The whole trick leans on one fragile fact. The leak has to be loud enough to hear in the first place. A tiny crack, a low-pressure main, a fitting that only weeps when demand drops. Each one whispers instead of hisses. Push the pressure down, and the signal syncs with it until it slips beneath the noise. And that signal is fragile over distance. The sharp, high-pitched edge of the hiss, the part that makes the timing crisp, fades first. Every joint, every T, every valve it passes filters it away until only a dull, low rumble survives. That's brutal on the big mains. A wide transmission pipe might only offer 2 access points hundreds of meters apart, and across that gap, the sensors catch nothing but a smeared echo. Counterintuitively, the smaller the pipe, the farther a leak can be heard. The giants are the hard ones. Then there's the city itself. Traffic, pumps, a humming transformer, footsteps overhead. The surface world is loud, and every bit of it fights the faint signal climbing up through the soil. It's why so much of this work still happens at 3 in the morning, when the city finally goes quiet. The math also assumes a single, clear voice. Put 2 leaks on the same stretch, or let the sound ricochet off bends and branches, and the correlator sees several peaks at once. It can lock on, with total confidence, to a spot where nothing is wrong. The more tangled the network, the more sensors it takes to trust the answer. And never forget what it actually hands you. A place, not a problem. It tells you where, never how big, never how fast. And only when you can clamp onto 2 points with the leak trapped between them. No hydrant, no valve, no bracket, no answer. Engineers learn to fight back against every one of these. But one adversary undid more of their work than all the rest combined. Not noise, not distance, not pressure. A quiet revolution, buried in the ground itself, the pipe. And then plastic happened. Modern pipes are increasingly PVC and polyethylene. Plastic is the correlator's nemesis. It's soft. It slows leak noise to as little as 300 meters per second, and it absorbs the high frequencies that make a leak easy to hear. The hiss fades within a much shorter distance, so sensors have to sit closer together, and crews drop hydrophones directly into the water column, where the signal survives best. But the deeper fix was a change in strategy. Instead of sending a crew out to listen now and then, cities made listening permanent. Small acoustic loggers are clamped onto hydrants and valves across an entire zone, and they wait. Each night, in the dead hours when taps are off and the network falls silent, they wake up and listen. Because a real leak never sleeps. It hisses 24 hours a day. Against the silence of a city at 3 in the morning, that steady sound stands out like a scream in an empty room. The loggers compare notes, flag the noisiest zones, and some even correlate with each other. A permanent nervous system, woven through the pipes, feeling for pain. Utilities pair it with one more clue: minimum night flow. If water is still moving through a district at the hour when a sleeping city should be using almost none, something, somewhere, is leaking. So, back to our wet street at 2 a.m. A crew clamps a sensor to the hydrant on each side. The correlator listens, slides the signals, and finds the delay. 70 meters from the first hydrant, they paint a small mark on the asphalt and dig one neat, deliberate hole. And there it is, a hairline crack in the pipe wall jetting water into the dark, exactly where the math said it would be. No street torn open, no guessing. One hole. A city can't see its own wounds, but wire it with the right ears, and it can hear them whisper. That's hidden engineering. Subscribe to Beneath the Wires. There's a whole world of it down here.